do something that's a bit unusual in a YouTube video. I'm going to put a picture on the screen and ask you to stare at it for 20 seconds. Keep your eyes fixed on the cross in the middle and try to keep them still. You can blink, blinking's fine, just don't move your eyes around. Keep staring at that cross. Now, while you're looking at this picture, your eyes are sending messages to your brain. Those messages are travelling down neurons or nerve cells from your brain to your eyes. And because your eyes are still, the same messages are being sent down the same neurons over and over again. Okay, I'm going to count you down. Keep staring at the cross. When I finish the countdown, I'll change the picture on the screen. 5, 4, 3, 2, 1. Keep looking at the cross. Now move your eyes. Hopefully, when I first flicked onto this second image, you saw it in colour. But as soon as you moved your eyes, the colour vanished. Well, that colour never existed. It was entirely created by your brain. This is a process called adaptation, and it happens because, as I mentioned, the same neurons are sending their messages over and over again. And just like if I asked you to do lots of push-ups, your arms would get tired, your neurons get tired when they're repeatedly activated. Neurons also use chemicals to communicate, and in some cases they can even run out of these chemicals. Both of these processes mean that the signal can no longer be sent. So why does tiring out a neuron mean you end up seeing colours that aren't there? Well, this is down to the way the eye detects colour. We have 3 types of cone cell in our eyes, which detect different wavelengths of light. The wavelengths they detect overlap, but roughly correspond to red, green and blue light. But the signals from these cells go through another layer of processing before they get sent to the brain. And this is what's known as an opponency process. It's actually easier for the brain cells to look at the differences between the rates of cone firing than to look at each cone's response individually. Neurons group colours into pairs, or opponents, which is why it's called opponency, and tell the brain about the difference between the two. One type of cell tells the brain about the difference between red and green, firing more for red and less for green. Another for blue versus yellow. Top marks if you notice that there's not actually a cone measuring yellow. The clever little cells work this out by adding together the activity of the red and green cones and comparing it to blue, which, unlike your paint palette, does actually make yellow. The last type measures white versus black, basically light versus dark. Our experience of colour is created by our brain comparing output from each of these sets of neurons. So if you look at a green apple, your green cones would be much more active than your red cones. So the red-green neurons would fire less than normal, and your brain would interpret that as the colour green. If you look at something pure white, all the cones are equally active and cancel each other out, so your brain sees no colour. And that brings us back to the illusion. While you were staring at the greenish flower in the middle, your green cones were very active, and they began to tire and run out of the chemical they used to communicate. When you went back to neutral, your red cones were sending more signals in comparison to the tired green ones. So when your processing neurons compared the levels of the two, it came to the conclusion you must be seeing red. So that's what you saw. Because of this opponency process, you will always see the opposite colour to whatever you've been staring at. Here's another example of visual adaptation. Stare at the cross in the centre of this image for a while. Can you see a green dot moving around? If you move your eyes to look at the dot, you'll see the lilac spots again. The green is an afterimage. It's the opposite of the lilac. So the cones in your eyes that respond to the lilac get tired, and when we switch to grey, they respond less. This signal is processed in the same way as if we were seeing green. So that's what we see. You should also have seen the lilac spots literally fading before your eyes, as the cells that were telling your brain about them became tired and stopped sending the messages. So just like us, even our cells need a break every now and again. Thanks for watching. Did you see colours appear? Let me know in the comments if it works for you, and also suggest any topics you'd like to see me cover. If you enjoyed this video, please hit like and do subscribe for more videos about mind-bending illusions and all sorts of tips and tricks about your amazing brain. And if you'd like to know more about the basics of how your brain cells work, check out my video on how neurons send messages. See you soon.